Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the Microsoft Research Visiting Speaker Series. I'm Deborah Carnegie, and it's my pleasure to introduce today's speaker, Professor Steven Strogatz. Professor Strogatz is really the math teacher you wished you'd had. He's the Sherman Professor of Applied Mathematics at Cornell University, a renowned teacher, and one of the world's most highly cited mathematicians. He has been a frequent guest on National Public Radio's Radiolab. Among his honors are MIT's highest teaching prize, membership in the American Academy of Arts and Sciences, and a Lifetime Achievement Award for Communication of Math to the General Public, awarded by the 4 major American mathematical societies. He also wrote a popular New York Times online column, The Elements of Math, which formed the basis of his new book, The Joy of X. In The Joy of X, Professor Strogatz takes us on a tour of the greatest ideas of math, revealing how it connects to literature, philosophy, law, medicine, art, business, and even pop cultures in ways we never imagined. Please join me in giving him a warm welcome to Professor Steven Strogatz.
Well, thanks very much. It's my first visit to Microsoft Research. I'm thrilled to be here. Also, it's a nice treat to... Is my microphone on? Yeah? Okay. So it's a nice treat to have an audience that I'm presuming is pretty mathematical. Normally, I don't have that luxury. So, in fact, I think what I'll be doing here today is maybe more a talk and a conversation. I'm hoping that if I ask rhetorical questions that they're not really meant to be rhetorical. They're serious questions for you to give opinions. That is, let's have a little bit of a conversation about the subject of math communication. How do you get, or how does one get ideas about math from elementary math up to, let's say, graduate school level math out to the public in a way that they would find interesting and maybe even joyful or beautiful? So that's the theme here. I suppose I should start by telling you a little bit about the genesis of this book, Joy of X, which I'm amazed to see is being sold for $10. That is a pretty good deal. I mean, they're gone? Oh, the $10 ones are gone. All right, I take it back. They're being sold for whatever their normal price is. Anyway, so the book grew out of the column that Deborah mentioned, which was The Elements of Math for the New York Times 2 years ago. And so it's a pretty odd thing to have a math column in the newspaper. There really aren't very many of those. I don't know that I know of any. And so you may be wondering, how did that all get started? I had written some op-eds for the Times over the years. I wrote my first book for the public in 2003. And at the time, the literary agent who represented the book talked to the editor of the op-ed page and said, would you consider an op-ed from this author of mine? And sure, it doesn't hurt them to consider it. They can always reject it later. So anyway, I sent something, and they did publish it. And I got to be friends over the years with this editor, David Shipley. So a few years ago, actually I can remember exactly when, because it was the day of my 50th birthday. He didn't happen to know that, but I was in New York, and he asked me to look him up next time I was in the city, and I did, and we ended up having lunch on that day. And he surprised me by saying, we would like you to think about writing a series for the page, as he puts it, for the opinion page. Would you ever have time to write a series? So I thought, that's a wild idea. What would that even mean? But as it happened, I had taught all my courses in the fall semester of that year, and he was asking about the spring, and I had the spring pretty open. So I said I could do it this spring. And then the first question was, well, what would a math series be like? So he told me what he had in mind, which was that he himself had gone to good college. He went to Williams. He, I think, was an English major. And he said he took math all the way up to calculus in high school, and he could get good grades in it. But he never knew what he was doing, and it didn't really mean anything to him. That is, it all felt kind of like, I don't know. I mean, he was just doing what he was told, but there was no internal sense of this is a fantastic subject or anything pleasurable. And so he said, I know that you mathematicians and people who like math say it's elegant, or you use words like beautiful or inspiring. And he said, I have no idea what you're talking about. And I think a lot of the readers of the New York Times don't know what that is. And so could you convey to the rest of us what is the joy of math, or the beauty of this kind of thinking? So that was the goal. And let me tell you a few choices I made along the way. And that's where I think we could have a conversation, because you might think that some of these were bad choices or good. And I'd be interested in, seriously, in your take on this. I think it's a really interesting issue. How do you present to the public? So, well, all right, the first thing was, how should it be organized? That is, what I suggested to the editor was, I thought it should be math in the news. That is, it is a newspaper, and so there's always math relating to, let's say, the economy or climate change or controversies about the census or whatever. You know, so maybe tie it to something in the news. He said, no, absolutely not. I don't want that. He said, I want you to start in kindergarten with what are numbers. Then I want you to do addition. Then I want you to do subtraction, and so on. I was shocked at this answer, because it sounded really pedantic, and it also sounded like the first thing any math professor would think of, to just begin at the beginning and grind forward through the curriculum. He said, that's exactly what I want you to do, but maybe go faster. Don't just leave us in elementary school. Let's try to get to something more sophisticated too, but definitely start at the beginning so we know where we are. All right, well, so here's what that looked like when I tried it. And by the way, so this series then grew into the book. There were 15 separate weeks in the Elements of Math, and the book has 30 chapters, so there's 15 brand new chapters. So well, I will read it anyway. I have a friend who gets a tremendous kick out of science, even though he's an artist. Now, you might notice something a little problematic with that first sentence. Yes, you're nodding, the gentleman there. What's the matter with that sentence?
Well, you're separating out arts and science and...
Yes.
In a demeaning way.
In a demeaning way to the artist.
The artist.
The phrase "even though" is the offensive. Yes. Yeah. I didn't mean it like that. This is the issue of writing for a deadline. Now, you have your own deadlines here, I'm sure, with actually producing valuable products. In the academic world, we don't do much of that. We just normally don't have deadlines. But so here I had a deadline each week. That was a new thing for me. And I regret certain choices. I'm not sure, though, how I would want to. I've thought about this sentence. Should I say, I have an artist friend who gets a tremendous kick out of science? That might be better. But there's a certain snap, and it's true that there's bias in this way of saying it. And some people complained in the comments. But all right, anyway, that's how it came out. And it's a true story. I do have a friend who gets a tremendous kick out of science. And he's an artist. Whenever we get together, all he wants to do is chat about the latest thing in evolution or quantum mechanics. But when it comes to math, he feels at sea, and it saddens him. The strange symbols keep him out. He says he doesn't even know how to pronounce them. That's true. I mean, if he sees something with sigma or an integral, he doesn't know how to read that. But no idea what he's even supposed to say, let alone what it means. In fact, his alienation runs a lot deeper. He's not sure what mathematicians do all day or what they mean when they say a proof is elegant. Sometimes we joke that I should just sit him down and teach him everything, starting with 1 + 1 = 2 and going as far as we can. Crazy as it sounds, over the next several weeks, I'm going to try to do something close to that. I'll be writing about the elements of math from preschool to grad school, for anyone out there who'd like to have a second chance at the subject, but this time from an adult perspective. It's not intended to be remedial. The goal is to give you a better feeling for what math is all about and why it's so enthralling to those who get it. So let's begin with preschool. And so then, now what happens to get out of here? Should I hit reader again? Yeah, hide reader. Okay. Hey, that's pretty good. That worked. All right. So I thought as a way in, I would show, by the way, the series was online, so I was able to link videos. This is what the series looks like if you go to the New York Times. And so this is a clip from Sesame Street that I had always admired. My kids had watched it in this video, 1, 2, 3, count with me. And it explains why numbers are helpful. So take a look at this. Oh, let me start at the beginning here. Now I wonder if I'm going to have a problem. Yeah, I had this. Oh, no, I'm not having a problem. Good.
I'll get it. I get it. Oh, man. Oh.
Oh, hold on. It's for you, Humphrey. Here you go.
Thank you. Yellow, furry arms, how may I help you?
We're hungry.
Well, what would you like?
A fish.
Fish?
A fish.
Fish?
Fish.
Fish?
How about you guys?
Fish.
Fish, fish. You got it?
Well, let me repeat that. Fish, 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 fish.
You got it.
Alrighty, be right up with that order, Mr. Penguin, sir.
Yum.
Ingrid, go tell the kitchen, fish, 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 fish.
Fish, 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 fish.
No. Fish, 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 fish.
Not that easy in order, but I'll get it.
Excuse me, Ingrid and Humphrey. I have a better way for you to do this.
A better way? What do you mean?
Well, I just think it would be easier if you, count the fish.
Count them?
Really?
Look, I'll show you. Humphrey, you tell me the order, and I'll count with you.
Alrighty. Fish,
1,
fish,
2,
fish,
3,
fish,
4,
fish,
5,
fish.
6. See there? See what I tell you? Now you know how many fish to send up. 6 fish.
Holy mackerel! This counting thing can really save a person a lot of trouble.
Yeah. Does it work on other stuff? Say cinnamon rolls?
Yep.
Cream pies?
Sure.
Spark plugs?
Absolutely.
Wow.
He did it again.
He may be the smartest person in the whole world. All right, Ingrid, let's go get those. What are they again?
Fish.
Fish. Haha.
Oh, Sheriff, we need 6. Count 6 fish.
Yeah, so there are 2 points that I like about that, which is first that one of the characters says this counting thing can save a person a lot of trouble, which is true, right? That's the first lesson that kids are supposed to learn, that numbers are efficient, shortcuts, instead of having to say fish, fish, fish 6 times. You could just have the concept of 6. But then comes this deeper point, which is when they say, does it work on other stuff? Does it work on cinnamon rolls? Yes. Does it work on spark plugs? Yes. Because 6 is more general than 6 fish or 6 spark plugs. 6 is abstract. Not to us, maybe, but it is, right? 6 is a more general concept than 6 specific things like 6 fish. And so, in fact, the concept of 6 is an abstraction from reality that you could ask philosophical questions about, like, where is 6? 6 is not really in the world. 6 is somewhere in the world of ideas, in the way that truth and justice and good are in the world of ideas. These are Platonic concepts that are transcendent above the level of reality. They're abstractions from reality. Now, what I like about that is that a lot of times you hear the word abstract used in a sort of insulting way. People will say, I don't like math because it's so abstract. I like it when it's real world. Yet, a lot of the power of math comes precisely when it is abstract, when it's general and can apply to lots of different things like cinnamon rolls and spark plugs and fish. So to me, this is a really nice introduction to the idea of the power of abstraction. And anyway, so in this essay, I tried to make this point and also connect it to this philosophical question of, are numbers invented or are they discovered? And actually, in general, is math, where is math in philosophy? Is it something that we're discovering, like the facts of science, or is it something that we're inventing, like the creations we make in music and art? And do you, here you all have probably thought about this question. Anyone want to weigh in on that? Do you have a feeling? Yes, sir?
So first, implicit here is a couple of concepts. One is the Arab numeral system, and the other one is the positional system, right? So we don't need to write like Roman numerals. So when you define a language, I think you invent it. You don't discover it. Maybe there is some edge case where you can discover a language of something, but it's invented, and it was refined throughout times.
Mm-hmm. So you're saying the representational system, like in this case, they actually counted with the Hindu Arabic system, 1, 2, 3, with the symbols we're used to. That surely was invented. Yes. We know that. What about the concept of 6? Like when they look at 6 fish, I don't know whether that's discovered or invented, but one example that I discuss later in the piece is, suppose that another room calls in with the same order. So just as many penguin want just as many fish. Then, so like just to cut to the chase, it's now going to be 6 plus 6, which we know to be 12. But, that's not invented. That once you have the idea of 6 and once you have the idea of addition to group rooms together, there's no logical freedom in the result. So in that sense, I think you can say that some of the truths of mathematics are discovered even though you've invented the concepts. Did you want to make a comment? Yes?
Yeah, I would like to return the question to you. Do you think logic is invented?
Well, that's a good, now you're really yes, now that's a good question. Right, that's right. I'm presuming that somehow logic is given. And you could say, no, it's not. If that's invented too, then it's all invented. Is that what you're saying is a possible argument? Yeah, that is a possible argument. I don't like it, I don't want to believe that. But of course there are alternative logics, so we know that you can, consider them. The logic that is the standard logic, whatever it should be called, conventional logic, seems to work pretty well in reality, and so that's the one that we use. But there's quantum logic and fuzzy logic, and so yes, this is deep territory. I don't want to spend too long on this, but for the purpose of the New York Times column, I took it that we're not going to question logic. We're just going to use the ordinary Aristotelian style logic. Yes?
I just remember when I went and I first did math in college, and pianos, axioms, starting real analysis, and I thought, oh great, we're going to be doing this really advanced mathematics, and starting with things like, there exists a number 1.
Yes, yes.
And having those basic assumptions, because if you don't have those basic assumptions to start with, you can't get all the other stuff. Mm-hmm. So I just found that kind of mind-blowing.
You liked that or didn't like it? Sounds like you did like it. I found it interesting, illuminating.
I liked the structure of it, yeah. But it did disappoint me that nobody could point to a purer truth of these things that were just self-evident.
Yes. Well, yes. It's interesting, all that. Yeah, you do have to start somewhere. I don't think anyone has found a way around that. Wow, this is all very interesting. I feel like talking about biblical references here, right? I mean, the beginning of Genesis in Hebrew starts with the second letter, not the first letter, Breshit. There's interpretations, why don't we start with the first letter if it's the beginning of the book? And so the old rabbis say it's because you shouldn't ask too many questions about the beginning. Just get on with your life. That's a traditional interpretation. That you'll be stuck if you worry about the beginning. And the letter itself is shaped like this, which sort of says, go that way. Go forward. I mean, anyway, that's a one rabbinical interpretation. But okay, this is not where I was thinking I was going. Okay, so that was the first column. And then the question is, would there be anyone who would want to read stuff like that? And it turned out that it got to be number 2 on the most emailed list for that week. And you can see up here in tiny 546 comments, which was a lot of comments. And most of the comments, I'd say like a really large majority, were along the lines of thank you to the New York Times and thank you to the author. I always had trouble with math in school, or I didn't really get it, and I appreciate having this phrase I use, second chance at math for an adult, really hit a nerve. Turns out there's a lot of adults who wanted a second chance. I didn't realize that. I mean, I had a feeling from my friend that there might be people, but there are a lot of people. So what's interesting about that, at least to me, is that when you look at typical pop math books, they're not addressing that audience. pop math books are popular are usually written for us, people who already like math and want to just learn some other part of it. But math for the people who need it the most, it's very hard to write for that audience. Not many people try. Anyway, so that's who I was aiming at. And well, let me give you an example or two of what I'm trying to do, both in the book and in the columns. The main thing, there was a question of a choice. Like, for instance, should there be proofs? A lot of people have trouble with proofs and the reasoning involved in rigorous math. Some would say you should focus on history. Like, people like to read about people, tell stories about the great mathematicians and what they discovered. I felt like, no, actually, I want to make people have the mathematical experience. That is, feel what it's like. Why do we get a thrill from a proof or a calculation or a picture? I want them to have a little bit of that thrill to see, because that's, I think, what drives people to do math. I mean, other than practical things, is the pleasure of it. And so here's an example of an attempt to do that. Let's see. Oh, yeah, here's where I get to do PowerPoint. No, I don't want to do that one. That was an attempt. Whoops, what happened? Oh, here I am. Sorry.
It's a feature.
Feature, yeah. Thank you. I knew it had to be a feature. This is where I wanted to start. So this was an attempt to discuss a problem that could come up in high school geometry, which is the area of a circle. We all learn in high school that the area of a circle is pi r squared, if r is the radius. And I defined pi for the readers in terms of the circumference of a circle divided by the diameter. That was the definition of pi. After reminding them what circumference and diameter mean, I addressed the question, how do I know it's the same number for all circles? It's an interesting, I mean, if you're really careful and sophisticated, you would ask that, how do I know pi is the same for a big circle or a little circle? I didn't give a real proof of that. I just said, you could imagine taking a circle and putting it on a photocopier, and if you scale it down, you'll shrink all distances. Suppose you shrink it by 50%. You'll shrink the diameter by 50%, but you'll shrink all distances by 50%, including the circumference. So the ratio will always be whatever, the same number. And I thought for that audience that might be convincing enough. Not a proof, but okay. But now, why is the area pi r squared if pi is defined in terms of circumference divided by diameter? So here's a proof. And what I liked about this proof was that it contains what I think of as drama. That is, in a typical drama, like on television or in the movies, things get worse for the hero before they get better. Right? The hero gets in trouble. And I feel like this proof begins immediately you feel like you're in trouble. So there's this circle. We're going to cut it into 4 pieces. And if we could rearrange those pieces and calculate the area of the new shape, then we could calculate the area of a circle. So I take those 4 and rearrange them into this strange-looking scalloped shape here on the bottom. And it looks like I made it worse. I mean, how am I going to figure out the area of this crazy thing? Well, okay, I don't know. But I can observe a couple of things about it. One is that this distance is the original radius, because that's just, how we defined radius, from the center out to the rim. And also, we defined pi so that this whole circumference would be 2 pi times the radius, or pi times the diameter. So here is 2 of the curved pieces. That's half the circumference there, so pi r. And then on the top, that would be another pi r. All right, so I have pi r as the arc length here on the bottom, and r for that length of that slopey side. And as I say, at the moment it doesn't look promising, but the thought would be, well, what if we took more pieces? So there's with 8 slices, and I stack them up the same way, and you notice now that the curvy parts are not quite as curvy as they were. It looks like it's trying to get flat. And the part that was slopey is now standing a little more straight up. That is, compare that one, that angle of that, to the next one. It's starting to stand more straight up. If we take 16 pieces, now it's really getting quite straight up and also pretty darn flat. And so you can see that what I'm trying to do here is teach the reader who doesn't know calculus that if you go to the infinite limit, things will become simpler. That is that most people don't have this intuition. The average person thinks that infinity is, mind-boggling. The idea that infinity could be your friend in math and could help you solve a problem, which of course that's the heart of calculus, is that infinity is being domesticated and tamed and becomes your ally. That's what I'm trying to show them here. That if I can take more and more of these slices, in fact, this shape will converge to something very simple. It will become a rectangle. And now we know how to find the area of something like a rectangle. It's just of course, this bottom, which has been pi r throughout the whole process, times this r, which is now standing straight up. So pi r squared, the area of a circle. So I don't know if you've seen that proof before. Isn't that nice? I mean, that is a totally elementary proof that any kid, I see a child there. Do you know about pi? So maybe, okay, that's a proof that I hope you could understand. I see other younger people there too. Yes, okay. Anyway, that's not usually a proof that's shown in school. I'm not sure why not. It's been known for thousands of years. It's an ancient proof. And what is so great about it is that I think it shows the idea of elegance, that you really now see why it's pi r squared. And it's just a very sweet little argument. And you didn't have to do any calculations either. I did think that the reader, just like my friend doesn't understand about symbols, I thought I should avoid doing a lot of explicit symbol manipulation. That was a choice. That I feel like for a lot of people, the symbols are a big hang-up in math. And so to the extent that I could use the power of the web and use color pictures and make it visual, that a lot of people might be less scared of that. Anyone want to react or say anything about that example before we go on? Yes?
There have been quite a few attempts in the last 10, 15 years to do more of a graphic novel approach or a comic book approach to teaching math. There was a really outstanding one that's sort of a life of Bertrand Russell, and I thought that was brilliant, gave it to a lot of people, and it kind of pushes your approach farther, but to a non-electronic or non-digital audience. Mm-hmm. Did you consider going that way?
So the book that's being mentioned was called Logic Comics. Some of you might have seen. It's one word, Logic Comics, with an X at the end. And you're right, it was a phenomenal book about set theory and paradoxes of infinity. Bertrand Russell is the main star, but there's Cantor and Frege. All these characters are in it. And it was told very dramatically against the backdrop of World War I and written in comic book style, graphic novel style. I did not ever think of that because the offer that was given to me was to write a series on the web. And I thought the web has certain advantages as a medium, like I could show that Sesame Street video, or also I didn't have the resource of a guy who could do the graphics like the artist who did for that Logic Comics book. So no, I never actually thought of that, but I agree that it's really a successful approach. What they did was remarkable. Yes? Gentleman on my left, yes.
So my wife, we went to the bookstore, my wife bought a book called Draw Yourself Smart.
Draw Yourself Smart, interesting.
It's about geometry,
yes.
Which geometry kind of lends itself to that. There's a lot of geometric problems, and the learning is very specific about, please draw these pictures yourself, encouraging you to do so, and I thought that was really interesting. And your comment about having a second chance at math, mm-hmm. I think that reminded me of that, of my wife buying that, because I think that was I'd like to, learn more about that. But the book kind of looks almost graphic and all. It does not look like a math book at all.
I don't know that book. That's interesting. Say the title again, Draw
Yourself Smart.
Draw Yourself Smart. Huh. That sounds interesting. Oh, yes. Did you want to make a comment?
My reaction specifically to your question on using symbols, and I haven't looked through your book, although everything looks fantastic already. So thank you. On that. But I think there's a big difference between making something easy and making something accessible. So yes. I would hope that symbols have their elegance because they encapsulate a concept after a lot of work. So yes. If you had something that was talking about, say, sigma notation or the concepts behind it, and then you ended it up by saying, here's the symbol, then that gives somebody an anchor to understand the elegance of it. And if you just do it without giving the symbols, then you've told a story but not given them the climax. So
Yes.
like a TED Talk on teaching, they say give your audience 2 + 2, don't give them 4, right? So if you're teaching, it's okay to make them work for it, just engage their senses first. And so I just have a little apprehension if you're saying you didn't want to teach them the symbols, because I think the symbols are the actual payoff.
Good, I see. Well, I think we're in agreement about that. I do, in fact, show some symbols and algebra for the same reason that you suggest, that they can be the payoff. Just like in this trivial example at the beginning, that 6 is the payoff for the fish, fish, fish. But also, as you point out, you want to really make it clear why you've introduced the symbol. That is, that they are your friend and a time saver and a concise embodiment of lots of ideas. But the reader has to be ready for it. That's what I think is often the mistake in the pedagogy, standard pedagogy, is that we're in a rush to give students answers and procedures, but to questions that they haven't thought to ask. So I want my reader to always be ready to ask the question before I give them the answer. So it does go slowly, but yeah, nothing wrong with symbols, absolutely. And there's one of the 6 main sections of the book is about algebra, including a pretty elaborate chapter on the quadratic formula, which a lot of people think of as ugly. And I really think it's a magnificent formula that does a lot of work. Yes, it's bulky looking, but it's solving all quadratic equations in one stroke. So that's a case where I did absolutely show the symbols and try to explain what they're about. Yes, you wanted to say something? Yeah.
Yeah. So returning to the idea of these very simple notions that we take for granted, like what is 6, I can see an astute reader perhaps being a skeptic, a healthy skeptic, and saying, well, what do you mean by area of a closed figure?
Yes.
It isn't a square. Implicit in this is, it seems, an assumption that, well, I can sort of divide it into smaller regions and I'll get the same answer if I add up the areas of the smaller regions as the original. But, people can ask things like, well, what do you mean by area?
Yep. Absolutely. These are very good points. Now, in my experience, very few people who are mathematically unsophisticated will ask that question. A reader who asks the questions that you just asked, what is area? How do I know that area is preserved when I move the pieces around? Those are the questions that only we think of. And we're usually pretty good at math already. I just think in practice that's not a serious issue. But I could imagine there could be a very brilliant reader who for some reason is naive mathematically, thinking of all that. And they might, yes, they would not be on resonance with this series, perhaps.
I think part of my point is, as people that are trying to convey these concepts, we have to be prepared to be surprised by questions that are as simple as, well, wait a minute, you haven't really defined it, or I don't really have a clear, I have an intuitive notion, but, can you describe more of the properties of area that would work?
But I think maybe you and I disagree a little bit. Yes, you need to be prepared for those, but I believe empirically that is not a serious issue in practice. That I think a lot of what we do as teachers is worry about that kind of thing and try to fend off those attacks or those serious and proper questions that are never coming in practice. And by doing that, we end up confusing the 98% of readers who just want to understand why is it pi r squared. And so we give, that is, the objection to the proof I just gave is it's not really rigorous for the reasons you said. We haven't defined area. I haven't proven invariance with respect to Euclidean motions and stuff like that. That's all true. But nobody, like my wife or the average person who not into math, they don't care about that. They don't even know why it's pi r squared. So I worry that in a lot of our books, we're so careful to be right that we miss the main educational point. So, I don't know if you would agree with what I'm saying or not. I think I try not to lie. I have a section of notes at the end where I do say what the gaps are in the proof. I think then I've got myself covered. Also, it's a real issue on the web because a lot of people are ready to criticize and do. And they put these criticisms in the comments. And so I would show each of these columns to my 4 or 5 smartest friends that are real nitpicking type of people. And they would pick. And that was a very helpful filter to go through. Okay, let me see what else might be fun to discuss. I do have one lesson that I feel like I learned through all of this, while we're talking about heuristics for effective teaching of this audience or not, that I want to share with you because it didn't occur to me, which is, what can you get away with? Like, how far can you stretch this audience? And here's a category, or let me give you two categories. There's familiar and unfamiliar, and there's concrete and abstract. And the example I just gave with the area of a circle, I would consider abstract. That is, it's about pure geometry of a circle. But it's familiar. People have all dealt with the area of a circle. So you can get away with familiar and abstract. The readers seem to like it, or can tolerate it. You can also get away with unfamiliar if it is sufficiently concrete. So as an example of that, I would mention when I had one chapter about conditional probability, which, the average person hasn't thought much about conditional probability, but I tried to tie it to a few real-world problems, such as a woman goes in for a mammogram, and she's in a very low-risk group. There's no history of breast cancer in her family. Her age is 40, she's fairly young, and her test comes back positive. The question is, after we give the doctor the statistics about what the incidence, what are the rate of false positives from this test, and what's the incidence for someone in her cohort, and that sort of thing, how worried should she be about this very scary result that she tests positive? And this is a real question that has been, medical students and doctors, trained people have been tested on this, and they give surprisingly wide range of answers. That is, they can't calculate the probability given the information needed to calculate the probability, which is kind of disturbing, considering that they have to make diagnostic recommendations about what to do. I mean, not just diagnostic, but what procedure should be done or not. And anyway, the correct way to think about it involves Bayes' rule, which, again, the typical person without much math training hasn't thought of. So in the rest of this essay, I tried to give a very concrete illustration of Bayes' rule by talking about the O.J. Simpson murder case. Again, this being familiar, but mathematically difficult, or concrete, I should say. So here's the story. I notice you're somewhat amused by this. It seems like an odd application, right? But have you heard this story about Bayes applied to O.J.? Let's talk about it then for a minute. So just to remind you of the details of the case. So it was back in 1994 that the football star O.J. Simpson was accused of murdering his wife, Nicole, ex-wife, I guess at that time. She was murdered by somebody. She was found dead with her throat cut, and also another person was killed at the scene, a friend of hers, Ron Goldman. And so O.J. was on, O.J., who had been a football star and a TV broadcaster and a movie star. Anyway, he was on trial for having killed his ex-wife. Now, the issue here was, that involves probability theory, was that he had a history of beating his wife, his ex-wife, that it was known that he used to beat her up. And she had called 911, the police had come. She had photographs with her bruised face. There was really no dispute that he was a wife beater and had a history of beating her up. But the question was, should this be admissible in the murder trial? And because it's not, this is, well, is it germane or not? Is it relevant? The prosecution argued that the jury should be told. They argued to the judge that this was relevant because it's known that when men murder their wives, they frequently had a history of beating them before they murder them. That is, a murderer in the past is often an abuser. But the defense said, you're getting that backwards. It's not relevant because if you look at the rate at which batterers murder their wives, it's very small. In a given year, according to the FBI crime statistics, in a given year, a batterer will murder his wife with a probability 1 out of 2,000. That is to say, of 2,000 women who are being battered, one of them will be murdered by her abuser that year on average, which is a small number, 1 out of 2,000. And so it proves nothing that O.J. was a batterer and shouldn't be admitted. It's prejudicial, it's irrelevant. Anyway, the judge in the case agreed with that argument and did not allow the jury to hear about O.J.'s history. And so my point here is that both the prosecution and the defense are thinking about this incorrectly. And a gentleman back there is nodding. Yeah, because here's how they should have looked at it. And this was pointed out in Nature magazine by a statistician named Good, I.J. Good. So he says, think of it this way. The things that you need to know about Nicole, the murdered woman, are first that she was previously beaten by her husband, and she was murdered by somebody. That is, she's not just a random battered woman. She's a battered woman who's been found dead, murdered. So those are pieces of prior information that we need to take into account. And so the correct calculation is to ask, suppose one other piece of information I should give you is, if you're just a woman, anybody, not necessarily a battered wife, in the year 1994 when she was killed, the murder rate in the US at that time for women was 1 per 20,000 per year. So let me run the numbers. We can do these in our head. What you should think of is, imagine 20,000 battered women and ask, how many of them will be killed in that year, on average, by their battering husband or boyfriend? Answer, I just told you a minute ago, it's 1 per 2,000 per year. So 10 of them will be dead at the end of the year, on average, from their batterer. 1 of them will be dead from someone on the street, a random, because the murder rate, assuming that their murder rate is the same as for everybody at large, which may not be right, but let's just suppose that they're not special in other respects. 1 in 20,000 will be killed at random. 10 in 20,000 will be killed by their abuser. So 11 will be found dead, 10 of which were killed by their boyfriend or husband. Okay, so the odds, if you're found dead and you've previously been battered, 10 out of 11 times it was your husband that did it. So there's about a 90% chance just on that O.J. did it. Now that doesn't prove that O.J. did it, of course, because there could be other evidence. He might have an alibi. There could be all kinds of exonerating evidence. It could also be higher than 90%, because his DNA might exactly match the blood at the scene. His footprint might exactly match the bloody footprint found at the scene. In fact, those things were all true. But so I'm not saying 90% is the probability he did it, but just on the basis of the prior beating, it seems like it could be argued to be relevant, and the judge should have. But okay, anyway, the point being that for the New York Times audience, this could be done easily in our heads. It was an easy calculation to walk people through, and the audience loved it. This was a very popular column. A lot of people said this was the most important column of all of them. Because, between mammograms and the legal system, this seems like this is real life and death stuff. This is where, and also the math is tricky and important. So my pedagogical point here was that you could do things that are familiar, like the circle, but abstract, or you could do very concrete things like mammograms and murder cases with unfamiliar math, like Bayesian probability, but you can't do both. You can't do unfamiliar and abstract. That's a conjecture. And I found out, I was led to this conjecture by a column I did about differential geometry. So let me show you that one and then I'll stop. I thought that people should learn about geometry on curved surfaces, not just geometry on the plane, because why not? That's where geometry has gone. So here was an attempt to do that. Let's see, there it is. Yeah, think globally, this was called. I always tried to have some kind of little catchphrase, act locally, think globally, except here think globally in the sense of global geometry. And so the first example I thought was harmless enough, and it was, which was, what's the shortest flight path from New York City to Rome? Rome is about on the same latitude as New York. that's a good geography question. A lot of people assume that Rome is farther south than New York because of the nicer weather. But no, it's not. It's due east of Rome, due east of New York. But if you've ever taken that flight, you know that the pilot hugs the coast of Canada for a while and then goes south of Ireland and into Rome. And I remember the first time I took the flight stupidly thinking that, you know, this must be because we're trying to play it safe. We're going to stay near Canada just in case the engine drops off, or we'll be near land. But that's not why we're staying near Canada. It's just if you hold up a real globe and look at it, you can see that's the shortest path. That's the effectively, well, it's an arc of a great circle would be the correct term, but it's the geodesic path, the analog of a straight line on the surface of the Earth. It does no additional curving other than the curving due to the curvature of the Earth. So it's not curving sideways, so to speak. Okay, so that's the generalization of a straight line on a sphere. But I thought, well, all right, let's really do something here. Because I had a video. See, this was the mistake. I had been told by someone that on the web you should build the column around the visuals. So figure out what you want to show and then write the words. And what I wanted to show was this video down here that one of my geometry colleagues had shown me, which is to figure out what the shortest paths look like on a surface. Can you see that thing? It's not, I don't know, it's a double-holed torus. Sort of a pretzel shape. I don't know how visible that is. It's kind of bright. You can see? Yeah. So here's now a movie in which a motorcycle is going to be driving without a driver with the handlebars locked straight ahead. No turning. This is to show that we're just driving straight. This is to be the analog of a straight line. So this motorcycle is just going to drive straight ahead at all times on this two-holed torus and watch what a straight line looks like on a two-holed torus. Let's see if this will run. I might have to reload the page. Yeah, sometimes these don't seem to run. All right, I'm going to risk. What would happen? Is that going to work? How do I do that?
Next to reader, there's a refresh.
Oh, good. Thank you. You guys are great.
You should give Windows a try. You don't have this problem.
Excuse me?
You won't have this problem under Windows.
No, I'm sure I wouldn't. Do you guys seriously prefer your products? No. I'm going to pause that because you get the idea that this is what a shortest path looks like on a two-holed torus. And I thought it was great. But my wife warned me. She said, this is really not good. This is not good. And I don't know why you like it so much, but I don't recommend it. And I just said, no, I think it's great. And she was right. The audience didn't like it. And one reader even wrote in a comment saying, the series has now jumped the shark. Now, I didn't know what that expression meant. Maybe I see some of you chuckling, you know. I had to look it up, and it so refers to the old show Happy Days, where the character Fonzie, you know, who dressed in a black leather jacket and is supposed to be a greaser, is water skiing, I guess, in his black leather jacket, and he jumps over a shark. And the point of the example with jumping the shark is that the series had been on for a few years. It had been successful. And then it started to get like it needed something new. The writers felt they needed to freshen it up. So they started doing absurd things like having Fonzie jump the shark. And so I was being accused of jumping the shark. And it was only in like the 6th or 7th out of 15 columns. And I didn't think I was jumping the shark. I thought I was just doing something fun. But anyway, this is my evidence that this example was so unfamiliar and apparently so abstract that even though it was visual, it was not, well, certainly wasn't successful with that reader, and in terms of how often it got emailed around and everything, it was an unpopular choice. So, I don't know. I think it's an interesting lesson.
Did you not feel cool as the fonts?
Did I not feel as cool as the fonts? I didn't after that reaction. I was trying to please the readers, and I still like it though. But that may be a sign of trouble. That is, the things that I found interesting may be at the wrong level. And so I should probably be showing them things more like the area of a circle or the OJ case.
Or sharks.
Or sharks themselves.
The probability for shark bite.
Very good. All right. So I think that's all I wanted to say. I'd be happy to take any questions that you have. Thanks very much. Yes, sir?
Just as a teacher and kind of mathematician, I lied earlier when I said I was an artist. I'm actually a designer.
Oh, you're a designer. Very good.
The difference between an artist and a designer is around the same as the difference between a mathematician and a programmer. So I think as a lot of generations are coming up, like right now I'm working on a problem with linear algebra. And so I'll get a book and you go through all the functions and you see all the mathematics and the matrix math and doing the tangents and normals and bitangents and stuff. But at the end, I have to go to the code first because my lingua franca is code when I'm looking at it. So I have to read the code and then I can loop back and understand these notations that I don't use every day, right? And I know I'm a very, well, not fringe case here because I think we're all in the same case. But as kids continue to grow, right, and they're learning programming as something that many, many people use, including designers. Some of these math concepts, that are we hitting that point where some of these concepts of computation almost need to shift to teaching it through code, because that's much more the practical applied mathematics first, then trying to teach them these symbols that have this rich legacy but are becoming more and more niche just to those who are studying the abstract mathematics.
Well, very interesting. I don't have a clear answer for you, having only taught it. Yeah, I mean, I'm still one of those people teaching it the traditional way, but I'm getting aware of the need to do more of what you're saying. That so many people, whether in quantitative finance or design or biotech, need to sit behind a computer and build software or run calculations that are being done by computers and not by people, or by people who have programmed, and to be teaching old-style pencil and paper math without that is kind of ridiculous nowadays. So clearly we want to be doing more of that, but there are so few of us who are trained. That is, the math training, pretty nearly everyone, let's say at Cornell that I'm most familiar with, I think almost no one in the math department can write a program to do even the most basic thing. There are some people, we have people that do computational algebra, and they really are computing things efficiently, and so there are people who see it as part of their day-to-day work. But I know from when the mathematicians teach engineering students who are big customers that they're very reluctant to include even something like MATLAB or Mathematica or canned stuff. Even that is a challenge because of the training that people get in pure math. In applied math, it's a little better.
As a follow-up, I used to have to teach, because I'm in between design and development, so I straddle that. So I used to have to teach math to designers back at the Art Institute. And it's kind of, if you like computers and you like math, you become a programmer. If you like computers and you don't like math, you become a web designer. That's kind of the crucible, but a lot of times they've failed through, at least in America, through high school. It seems to be this filter that we're going to force it to you, and if you're of this particular mindset,
force it math.
Yeah, force these concepts without telling you the story, without teaching you the mystery, without anything. Just here's all the stuff you've been through calculus. If you make that cut, you can learn the really cool stuff like translated numbers up there. But if you don't make the cut, you're going to think you have to become a designer, right? And so how I normally have to do it is here's what sine, cosine, a tan 2, this is what it looks like, right, as designers, right? Here's the scripts, you start visualizing this, here's the animation loops. And most of the time, some of these kids, I mean, not that they literally cry, but it would just blow their brain because they had been taught by high school that they were not good at math, and they had computational dispositions. They just felt that they were not good at math.
Yeah, this is a really important point for the whole educational system, that we need to be doing more of that. And it's not only, I guess I would amplify what you're saying, that students are sometimes learning not just they're not good at math, but how boring math is. That's what really kills me. I see my poor daughter, who's 12, learning something now called the order of operations, which is what, multiplying comes before adding, et cetera. Okay, we agree that we need a convention and there's a logic to the way we do it. That's all fine. I don't have any problem with the order of operations. But when you look at her homework, which might be on the order of 50 problems involving very long strings of pluses and exponentiations and so on, that might have, like 10 or 12 terms, and she's got to do 50 of them, and they don't have parentheses in them. We would never write that. There's no meaningful place that this would ever occur. And it makes me mad because I could see how she's suffering through it, and she thinks this is math, and I tell her that's not math. They're not teaching you math. And some moron who doesn't understand math is making this. Oh, are you taking that now? Do you have order of PEMDAS and stuff? A young person is raising.
I'm in Algebra 1.
Yes.
I'm 12 years old, just like your daughter.
Yes.
Do you think that things like this applying to kids like me and my friend here who's also in the same math and age, do you think that would also apply to us if they could relate that to real problems and also and things like how you turn the circle into the square? They could do things like that. Do you think that would change our opinion of math?
But I want to ask you. Yes, I think it might help. But because I've shown some of these to my kids and they seem to like it. By the way, my kids are not particularly mathematical. They like looking at Vi Hart's videos on YouTube. Some of you may know her stuff. Do you know her? No, okay. But they're more arty than mathy. My wife is very arty. But I feel like these are beautiful ideas that, yes, young people could enjoy and should see. And so, like another example would be you can do the Pythagorean theorem by making pictures of triangles and you put squares made out of crackers on the side. And you can count the crackers and then you can eat the crackers when you're done. And it's fun. You can do math with other kinds of food. You could look at Fibonacci numbers by getting pine cones and drawing spirals on them and stuff. I think that makes the point that first, math is fun. It's related to art. It's in the real world. And so I like doing all that. I think kids like it. But what do you think? Do you have an answer in mind when you ask the question? Or you just mean it as a question?
I was just wondering your opinion.
Yeah, okay. Yes, sir, in the back corner.
I think that your dichotomy between art and science or art and math goes to what he was saying, but also goes to what you're trying to do here, which is there really is no dichotomy between art and science and math. Mm-hmm. Most artists I know, especially younger ones, are immersed in some area of science and technology in terms of, say, the melting point of specific metals in order to achieve a certain effect. Or using electronics, writing some software, even, say, formulas for paint, for pigments. They have to think about it, but they're not math literate. So they're at that level of the web designer versus the coder.
Yeah.
They can only go so far because of that sense that they've been shut out of mathematics. That's the way it seems to work to me.
Yeah, I hope I didn't make that dichotomy sound like something I either support or really believe in. In practice, they do feel like worlds that, maybe you're right, that there may be a world I'm not seeing that's a younger generation or something where these...
Older artists are the same, but it's much more common among younger artists to whip up a piece of software or use some high-tech equipment in their piece.
Yeah.
And they have to understand how it works, but they may not understand the math behind it. And that I think is a limitation. It's like being a barefoot doctor in the old Chinese sense. You know how to do an operation, but you would never be able to explain why.
Yeah, what I like about to me, it feels like emotionally, the practice of art and the practice of math have a lot in common. As I say, my wife is an artist, and a lot of the artistic impulse, and also the feeling of struggling and being stuck. You have an idea you're trying to get out, it's not working properly, and the frustration and then the exhilaration when sometimes you make a little progress. This to me feels very like a shared experience that artists and mathematicians can, we can relate to each other perhaps more easily than people in other, I don't know, like, so to speak, real world I don't know that artists and, let's say, venture capitalists have that much in common as an artist and a mathematician. I don't know. I don't know venture capital people. We shouldn't pick on them. It just feels to me like we're both a little bit otherworldly in art and math, at least for the pure mathematicians. Okay, let's take some more on that side of the room. Yes, sir, on the far end.
So I just wanted to get your opinion on, there's an idea floating around engineering education at the university level now where they've noticed that a lot of students drop out after the first 2 years, and they figured out it's because they get hit in the head with 2 years of math and physics immediately. And that's not something that they're used to. So there's this thought that you start them doing some design stuff, you know, the fun stuff first, and once they get that, then they want to learn the math and physics to figure out why they did it the way they did it. So I just wanted to get your opinion on, you know, do you think that could work at a high school or middle school level for math? You know, just to reverse, to give them a reason to want to learn it. You know, have
the way you're describing it, it sounds like it could be a good idea in that it fits with this educational philosophy that I touched on earlier, that I feel like we give answers before students are ready to ask questions too often. And so when you mention that we hit them with math and physics in the first 2 years and it's not fun and it causes them to drop out, I think it's because we're giving them a lot of answers and techniques to questions that they haven't thought of, for the most part. So it could be that by having hands-on design experiences, the student might start to ask those questions on his or her own. And then, so yeah, I mean, in principle, it sounds like it could work, but I don't know. It's an experimental question. I guess it has to be. Do you say people are trying it now, or they're considering trying it?
Floated around. I know there's the University of Illinois, my alma mater, is looking at it because they realize that something like 40% of our students that enter as freshmen don't graduate in engineering.
Right. So part of it, I think, you know, a different way to look at it is not that we need to reverse the order. We just need to straighten out how we're teaching math and physics. That is, they could still come first, but they just have to be done in a better way. So that may be a different solution, but it's probably worth trying this thing that you're.
It's also, like, part of that thought is not just that we're teaching it wrong, but that it's actually used as a filter.
You mean deliberately?
People teach giant 300-person survey courses, and it's sink or swim, and it's thought that the people who swim will be the ones that deserve to be in the engineering program in the first place. Instead of thinking, you know, maybe with a little bit more effort, smaller class sizes, better teaching, whatever, we could get people, you know, into an engineering program who otherwise would be filtered out by by hitting this giant wall. Yeah.
Wow. I hear you, and maybe it's true that it is deliberately used that way. I would hate to think that, but you may be right. And partly why I hate it is because I was almost filtered out by that filter myself. Not exactly that one. I wasn't an engineering student, but as a freshman, I took the freshman whiz kid linear algebra class. Well, every good university has such a class. It's for the kids who took BC calculus, got a 5. They're sitting there. What math are they going to take when they hit freshman year? So they give them a very rigorous linear algebra course where you're supposed to learn how to prove things. Usually it doesn't include many pictures, doesn't include software. It's very abstract the way it's presented. And so I took that course and was getting wiped out by it. And it made me think after it was over, okay, I don't have the right stuff to be a pure mathematician or any kind of mathematician. And that might be correct, but but I did love math, and just through whatever reason kept taking it. And then the next year I had a complex analysis course, which I could suddenly understand again. That felt like calculus, except with complex numbers, but I could do that. And when I think back on what that freshman year course was, I think it was what you're saying. It was the math equivalent, that the math department doesn't want to be too big. We don't want too many majors. And we're going to filter out the people who thought they were good in math in high school, but they don't have the right stuff. And so I think I was identified as one of those people without the right stuff. And I don't think it's really true. There are various types of right stuff. There's a talent for pure math. There's a talent for seeing connections and then becoming an applied mathematician. Or, you know, there are visual people. There's algebraic people. There's analysis. I mean, there's a lot of different ways to be good at math. There's also computing, people who are computational. So it burns me up to think that they're deliberately filtering people out. I don't really imagine that. I just think it's laziness, that it's more efficient to have one professor and have a big lecture, and it saves money, and but maybe it's more malicious than that. Yes, sir.
I was surprised that you didn't complete the
we should stop after maybe one more question?
Surprised you didn't complete the O.J. Simpson calculation.
Didn't complete it?
Yeah, maybe you did in the column.
Oh, what else do you want?
More data that needs to be there.
Oh, yes.
Because the question was, is this evidence prejudicial?
Yes.
And to answer that, it seems you would need to know for murdered women who are in a non-abusive relationship, what fraction of them were murdered by their partners.
Oh.
And if that is also 10 out of 11, then it really is prejudicial.
Oh, hold on. Let's see. No one's ever made this point before. So you say murdered women who are in non-abusive relationships, but they may also be murdered by their partners. That is, the partner until that point had no history of abuse, but because of the kinds of passions that happen or whatever, you don't have to make an explanation. There's just a statistical point that often the husband did it. And that we should know what that rate is too. Oh, good point.
If it's the same, then the abuse.
If it's 9 out of 10 that the husband always did it, abuser or not, then what? Then
the evidence is prejudicial.
Because the battery would have no bearing. It's 9 out of 10 either way. Except that would be worth knowing that 9 out of 10 the husband did it. Which is probably what the police usually think anyway.
He was the husband, so they had that information.
But the question is it relevant that he was a batterer or not? I mean, you're saying, whereas your point would be, is it relevant that he's the husband or not?
No.
And it might, no.
No, the point is it relevant that he's the batterer? Because if battery doesn't increase the probability, then it shouldn't be admitted.
Yes, you're right. So that should be included. It seems like the FBI should have that data. That is, of how many murders were with people with no prior record of that. And you're right, that's a very nice, that number should be taken into consideration. I didn't include it. It wasn't in any of the articles on this. It's an interesting point. Good. Did we have time for one more, or should we stop with that? Okay, I think I took one from you before, so I'll let that gentleman go.
Okay, so sort of going off what he was saying.
Yes.
You've written an awesome article about the O.J. Simpson trial. Lots of people have read it. They're intrigued. They can see how math can improve their lives and just sort of society in general. How do people that read that take that away and then themselves become people who can analyze the world around them using the different principles that have been demonstrated in that article? For example, if the jury themselves had those analytical capabilities, it would be completely different from needing to bring in other people to try to sway one way or the other the whole court system in that case.
Let's see if I get the question. So you're saying, I'm imagining my reader. The reader has read this column, which is a little taste of math. It's 1,500 words, and they're now not suddenly statistically savvy. They're just the same reader they were, except they read this column. And now maybe they know a little bit. Now I do have footnotes that say if you want to learn more about either the legal system or conditional probability, here are different references. Maybe if some small fraction of them are interested enough to go do that. But even if they did, then you're saying that, so what? I mean, so...
Can I clarify?
Yes, please.
So what are opportunities that we can do as a society to make all of these concepts in general more accessible? This is just the beginning, but what do you think the next steps are in general to make these concepts more accessible to the public?
What are the next steps for the society to make these concepts more accessible?
You should all buy his book.
Well, I don't want to say that. I don't think that would help so much. I mean, what I guess I'm hoping with the book, that question I have, that may be a better answer, is that people will be more open to teaching themselves more and getting more sophisticated across the board about quantitative reasoning or math in general. Partly it's the informed citizenry argument to be able to think about the issues that face us. Partly it's just the pure hedonism argument that your life is richer and better the more things you know and understand, whether it's music or art or math or anything else. But in some system, you know, like at the societal level, what is there to do? I don't know. When do you, people are out of school. You could hope that the media, I'm not sure what to say. I don't really, I'm kind of just floundering with your question. I guess I can only imagine that people will have to take it on themselves. First they have to get curious, then they have to find the resources to learn, which there's a lot of good stuff on the web and there are a lot of books being written and people that they could talk to. I think the first has to be the spark of curiosity. So if I can spark a little curiosity, I hope that people can help themselves. But I haven't really thought about your question. It's really important. Okay, thanks a lot, everybody.